information-based security in India Sacre.
Sacre, Latin sacre?
Sacre, not sacre. Sacre, L-A-Y.
Oh, sweet.
That's a correct one? Okay.
Thanks, Selim Costa.
You got one too?
Huh?
Oh, you can choose now. I'll go for the black one.
Yeah, good, like 2 on 1. I quite like that one.
You want?
Yeah, okay, just in case it doesn't work. Thank you.
So I'm going to speak about the relation between concepts called the differential privacy and quantitative information flow, which is what you have seen in the first 2 lectures this morning. Okay, so what is differential privacy? So this is a concept that arises from the field of statistical databases. It's due to Cinzia's work. And well, I don't know in which paper it was proposed the first, but it became very famous after having invented the talk entitled 2006. And nowadays it's very, very popular. I mean, it's really a hot topic in statistical databases and in the field of security in general. Okay, so let me introduce the problem. So by database we intend simply well, all possible sets that you can form taking a collection of individuals in a set from some set U and assigning to them some values from a set of values y. Okay? And then you have you want to do something with these databases. Typically you want to query them. So you have a function which is a query. From this set of all possible databases, let's call it X, to a set of possible answers, let's call it Z. And this can be anything, right? It can be, for instance, if the database contains the height of all the individuals in the database, then this F could be, for instance, the question, what's the average height of the people in the database? And the question of privacy arises from the fact that you would like to make sure that the values of the individuals are kept secret. And if you have a query like the one I just explained, there might be a problem because in general, if you know the value of X, the value of the query in the database X, and then you add another row to this X, this R represents an individual, and then you compare these two. If you know the number of people which are in the database, then you can infer the exact value of the height of this new individual. Okay, so this is one of the problems. Another problem is that maybe you want to hide. Some people are willing to participate in the database, but at the condition that nobody knows that they are about their presence in this database. Okay? And this again might be a problem because, for instance, if all individuals have height between, say, 160 and 180, and there is one particular individual which is 190, then if you ask the average height, if you apply the query to a particular database and the average height turns out to be more than 180, then you're sure that this individual, this particular individual, is present in the database. Okay, so a solution that has been around for 10 years is instead of giving the exact answer, you give a randomized answer represents the randomization, it represents the function f plus some noise, okay? So the randomized version of f. And of course you can imagine it as a channel from X, Z. And now the question is, okay, so can I randomize the version of f, but I still can guess the value of the individuals, still can retrieve, still can try to retrieve the value of x from the answer z. And depending on how k is defined, the probability of guessing right might be relatively high. Right? So this is related to the one try attack which Costas was speaking this morning. So the notion of differential privacy, which was proposed by Gort, is an attempt to measure how good is the function, the randomized function k with respect to privacy. So we say that the k is epsilon differentially private, where epsilon is a constant greater than 0. If and only if for every set values z, I'm giving you here the most general definition. In case z is a discrete set, we could just take individual elements of z. So anyway, if S is smaller than Z, is a subset of Z, and for every pair of databases, X and X prime, which are reactions, so I write it like this, meaning that they differ by only one row. So differ just in one entry, either the value of this entry or because the row is not there, because the individual is not there. In one case it's not there, in the other case it's there. So for all these cases, the probability that the answer is in S, if the entry is X, is equal, differs from the probability that Z is in S, in case the entry is X prime, for at the most a factor E at the power of epsilon. So in practice, this means that well, actually, in the rest of this talk, I will only consider the discrete case. So, in the discrete case, I can just rewrite this as the same property, but for single elements in Z. So,
I'm a bit confused by your notation. So, one of the Z is a set of answers, the other Z is a single possible answer.
Sorry, no, the Z is just the random variable. Like when you write z equal to small z.
But you have a set of Z. You quantify for all a subset of Z.
Yeah.
That
Is
is
a
the same
different Z.
This is the carrier.
This is calligraphic Z.
Calligraphic, yeah, sorry. So this is the random variable and this is the set values. So anyway, I'm going to rewrite it for the discrete case. So this means that for every small z in calligraphic z, the probability that we get this z as an answer when the input is x divided the probability to get the the same answer when the input is x prime is bound on one side by e to the power of epsilon, on the other side by 1 over e to the power of epsilon. That's for all x and x prime which are adjacent. Okay, so I will use this definition. Now, intuitively, the smaller is epsilon, the better privacy we have, because we make, well, the more noise we have, right? And in the limit, if epsilon is 0, this is 1, this is 1, that means that all column of K seen as a matrix will be the same. So for every Z, the entry for x and for x prime have to be the same. So it means that this channel is completely noisy. The channel with capacity 0. So this would be very good for privacy, but not very good for. It would be completely useless. So it would mean that K gives a completely random answer. So, the motivation for our work is to see that whether we can use quantitative tools that we know from quantitative information flow to try to explore the trade-off between utility and privacy. And note that it's an interesting question in the sense that privacy is not exactly the negation or the opposite of utility, because utility refers to the difference between Z and the real answer to the query. Okay, so when I see Z, I am interested in guessing what is the query, what is the result of F. I'm not interested in guessing X. Whereas privacy refers to X, actually refers to particular pairs of X, not even only to the adjacent ones. But anyway, the thing is that if this is my K, this is my Z, and this is my X, the privacy refers to the difficulty in inferring X when I see Z. Or I would say, let's not use the word privacy, because privacy is a bit more specialistic meaning because of this reference to the particular information of an individual. Let's call it a leakage. So leakage in the information theoretic sense. Whereas the utility refers to what I get after I apply F to X. So let's call it to Y. Okay, so utility would be the difference between Z and Y.
What is this word you're using? Utility?
Yeah, utility. I haven't not defined it yet. I define it formally later, but intuitively that a randomized mechanism is more useful if the answer you get allows you to retrieve the real answer with a good probability of success.
And the goal is to try and design these things so that the utility is high and the privacy is also
exactly.
high.
Yeah.
And that can be done independently of F.
Well, no, of course not. So first of all, let me say that we are going to restrict ourselves to the case in which K is so-called oblivious, which means that we can really decompose K in these two parts, where the F is the query, which in principle usually is deterministic, but it doesn't it doesn't matter in our framework whether it's deterministic or not. So anyway, it's a channel. And then we have another channel which introduces the noise, all the noise we need to guarantee differential privacy, epsilon differential privacy. And however, the differential privacy is not on Y but on X.
I'm prepared to be in touch because right now I'm looking for this.
Oh, okay. So anyway, the questions that we have explored in this framework are, so first of all, first question is what's the relation between leakage and differential privacy? Or in other words, does the epsilon differential privacy property implies a bound on leakage? And we will see that the answer is yes. Of course, the reverse is not possible because I can have a very high leakage with an infinite epsilon, because I could have the case where one row I have 0 and the other I have 1, or value delta very small, but still higher than 0, and then epsilon will have to be infinite. But the fact that I have a small difference here doesn't mean anything in general for leakage. So the interesting question is all in this direction. Question 2, what does it imply from the point of view of the leakage for one single taxon? This picture here, the leakage is between is on the information stored in all possible databases, but in fact the focus of differential privacy is not in hiding the content of all the database, but just the content, the value of a single individual. Question 3 is epsilon differential privacy implies a bound on utility. And we will see that also here the answer is yes. And finally, the most interesting question is whether we can figure out a technique to build the optimal utility for a given level of privacy. Optimal utility H. Or under the constraint that the whole thing satisfies epsilon differential privacy. Okay, so I'm going to, what time is it? 12. So about half an hour. So I'm going to,
40 minutes.
So
10 minutes for each question.
I'm going to start with the first question, which is the most challenging one. And it's not the most interesting one in my opinion. Actually, it's the least interesting one. But the technique is general, and then I can reuse the same technique to answer all the other questions. Okay, so first of all, I wanted to give a better formalization of the representation of the databases, addressing at the same time the two problems of privacy, namely the value, protecting the value of an individual and protecting this presence of or absence in the database. This can be done simply by taking a new domain of values, where I have the standard ones, plus a new one, say bottom, which represents the absence of the individual. And then I have the set of individuals U, So the universal databases X will simply be all the possible values for each individual. Right? So V at the power of U. And the adjacency relation can be seen as imposing a graph structure in this universe, where adjacent means to be connected by an arc. So, for instance, if U is, say, we have only two individuals, 0 and 1, and V is ABC. So I have three possible values. Let's say that A is the bottom. Then I have a database of 9 elements, sorry, a universe of 9 elements, which are AA, AB, BC, VA, BC, CA, CC, CC, and they are related like a grid. Also, the extremes are related, so it's like dots. Okay. So this is a graph structure, an undirected graph. So that's nice because we can speak about the notion of distance and automorphism, which will be very useful in a moment. So I'm going to start with question number 1. So is there a bound on leakage? And the answer is yes. And the way to prove it is the following. I mean, the way we have proved it is the following. Suppose we start with a certain matrix 0. So this is I'm going to use matrix just because I'm more familiar with it. So this is our A. Well, let's say, just start with A0. No, let's use M. I need the K for index. Okay, so let's assume that I have at least as many columns as rows. So I'm going to transform this into another matrix, say M, which has the property that all the I elements for each column are on the diagonal. Let me remind you that the leakage here is the Smith mean entropy. So is I infinity of x z defined as the mean entropy of x minus the posteriori entropy of x given z. Okay, so and this is so at h infinity of x is simply the log of the number of elements of x. So n is equal to the cardinality of v, the power of the cardinality of v, small v and small. Okay. So this is the log n minus plus log so h of x given z. This is the log of the summation of the max for every okay, I sum on all possible z, the maximum of the joint probability Px Okay? And if I consider the uniform distribution, which is the worst case of leakage, is known to be the worst case of leakage, is also, I can simply consider the max of each column in the matrix. Okay? So this will be in the case of uniform input distribution, this will be the log of 1/n for the summation of the max of P of z given x. So this means that to compare, to reason about leakage, in the case, in the worst case, I just need to consider the summation of the max of each column. Now, I'm going to make this transformation in such a way that if this is epsilon differential private, also this one is epsilon differential private, the mean entropy is the same. And all the maximum of the column are in the diagonal. The reason for doing this is because I need to transform the matrix, the channel, in such a way that has a very regular structure, so I can find the bound more easily. And this part does not contribute to the leakage, it is 0. And then I'm going to make a second transformation. So this is transformation number A, this is transformation number B.
So what are you allowed to do when you say transform? Just interchange rows and columns?
Oh, I can do everything provided that I maintain epsilon differential privacy. And in principle, it's sufficient that I have this relation. At the end, I will find an array, a matrix, which n prime, which has a reasonably simple way to compute the bound. Okay, so this one has the property that is also epsilon differential private, is at least as much leakage, but in reality, for our transformation, these are all equal. And the elements here are all the same, and that's still the maxima. Okay, so let me start with the first transformation. The first transformation actually is quite simple. So essentially what we do, so for every column we are going to look where is the maximum, suppose that is here. If the maximum is on a row X, if the maximum is on the row Z, which has not been considered yet, then I associate Z and X. Okay, I'm constructing an isomorphism, sorry, a projection from columns to rows, in such a way that the M of X Z is equal to the max of the column Z. Okay. So I just start from the first column and I consider one by one each column, and if I can make this association, I do. if I am in the case in which the maximum has already been taken, because it's already been associated with the earlier column Z, then what I do, I accumulate, I sum, I practically change this column, I collapse this column into this other one, and so I put the summation here of what was before and this one for all elements of the column. So the maximum here is remains the same in the same column, and this one becomes all zero. Right? Is replaced by zero. Of course, this transformation preserves epsilon differential privacy because it's a linear combination. So the ratio between two elements here remains the same because I'm summing things which also preserve the same ratio. And for the leakage also doesn't change anything because will be considered here. I mean, instead of being considered here and here is considered only here, but it counts also for this one. Okay, and then once I've done this, then I have all zeros here, so I can just choose a new row which has not been considered yet and make the association to this new row. Okay. So this is the idea, and of course in this way I will construct an isomorphism because a bijection because I have at least as many columns as the row, so I can always complete this construction. So at the end, and to put them in the diagonal, this is not really necessary just for making things more understandable. So to put them in the diagonal, I just permute the columns at the end so that the bijection becomes the identity. Okay, so this is done. Now the construction B is much more difficult. And this is something that I cannot do in general for every graph. I need the property specific of this graph databases. And the property is a property that we call VT++. VT stands for vertex transitive. The plus plus is the bias because it's stronger than vertex transitivity. So what?
Maybe send email somewhere.
It was ironic. So VT++ means that there exists n automorphism, sigma 0, sigma 1, sigma n minus 1, graph automorphism. Such that for every element x, if I apply these automorphisms to x, I get the full space of databases, I mean the full domain. Sigma 0, sorry, the set of sigma k applied to x for all k between 0 and -1 is equal to x. Okay, so this is stronger than vertex transitivity because vertex transitivity only, it's a weaker property that only says that whenever I have, for any pair of vertices x and x prime, I can find an automorphism sigma that maps the x into x prime. This is much stronger because it requires that I can find a set of automorphisms that make the vertex transitive, and this set has cardinality n. So this structure databases has the property
We didn't exactly write down what is the this relation there. It might be confusing. Maybe we should.
Well, it's okay. Yeah, I made an example. It's clear the example.
Okay. I mean, if the
So you should.
Okay.
Yeah. So you just change one. So this is a set of tuples, right? U tuples with the values in V, and you just change one element in the tuple with any other value. Okay, so this is Vt++, and the set of automorphism can be constructed in the following way. You take any permutation row in the values.
The graph is constant degree.
Constant
Constant degree.
Constant degree.
Yeah.
Yes.
It's exactly U.
Yeah.
And every vertex looks the same.
And notice, however, so we tried the first with another property that was to have an automorphism with an orbit of cardinality n, with a unique orbit, but we didn't succeed because this does not have that property. Because in the worst case, this is the n cube, if v is equal to, this is just the set of binary strings, which has an hypercube structure, and does not have an automorphism with just an orbit.
So the configurations of Rubik's Cube have exactly this property, right?
Yeah.
Yeah.
Okay, so to construct the group of automorphism, we take a permutation on the values. And then we construct, so this set of automorphism that I wrote before, sigma 0, sigma 1, and so on, just constructed by taking any possible tuple, U tuple of rows. So this row is a permutation of the values. I take any U tuple with repeated applications of this row. So K0, K1, Kn minus 1. So meaning that whenever I apply this to an element of my universe, say A1, A0, A1, In, minus 1, I get the element, I map this into the database, which I obtain by applying row K0 to A0, row K1 to A1, and so on. And it's easy to see, well, maybe not so easy, but it can be proven that this set of automorphisms gives a Vt++ property. Now, what's the idea of doing that? Well, essentially, I use this to make the following transformation. In order to make this diagonal all equal, I just make the summation, the average of all the elements on the diagonal. But of course, I have to make sure that this is okay, so I have to make an analogous transformation on all the rest of the array. And I have to make sure that the epsilon differential privacy is preserved. So one way of doing this is taking all the elements that have a distance, say k, from the diagonal, and making the same average on them. And this is not as simple as it looks, because the adjacency relation is not simply from here to here, so it's rather complicated. So anyway, the definition is that m prime x z is defined as 1 over n, the summation of k goes from 0 to n plus 1 of m x, sigma k x this sigma k is one of these elements, these automorphisms that we started before. And now we have to show three things. One, that the maxima are indeed in the diagonal and that they are all equal. This is easy because on prime x is equal to 1 over n summation 3, 0 to n minus 1 and sigma k x sigma k y x. But since these are all since these have the property of generating any element of the domain, I can change this into any other element, for instance x prime. So this is the same as 1 over n. And sigma x prime, which is equal to 1 over n. No, sorry, to m x prime is prime, m prime x prime.
So it's like a group as written trick.
Yeah. And of course, this is the maxima because I'm taking an averaging over the maxima. And 2, I have to show that this is distribution. Or let me show first that the epsilon differential privacy is preserved. So n prime x z, which is 1 over n, because this was differentially private, I can write that this is you can take any other element here. Times here the power of epsilon, right? So this is the, I'm using the epsilon differential privacy over m, which is m x prime and the last thing is to show that this is a correct distribution. Namely, that if I sum for every z m x z, I get 1 in time. I get 1. And this can be also proved rather easily because this is equal to this. And now I interchange I commute the two summations, and I get 1 over n k z m sigma k x sigma k z. And here I use the fact that these are automorphisms, so this generates by changing a z, I get every element of the domain. When I make this summation over z, here I get all possible vertices. So in fact, this summation is the summation on the column, on the row sigma kx, so it's equal 1. Okay, so this is essentially all what needed to prove. Now we have this nice matrix. Now I can prove the bound. How much time do I still have?
12 minutes.
12. Okay,
By the way,
so
the truck is
bound
there
very
if you want
easy
to buy.
prove. So we just take one line. So the line is of the form a plus b1 plus b2 is 1, and I know that is 1. And now I use the fact that there is this property of epsilon differential privacy. So I know that if I consider the elements which have a distance 1 from the diagonal, say, suppose that this is distance 1, I know that these have to be greater or equal to A divided to the power of epsilon, because of the property of differential privacy. And the same with those of distance 2, except that those will have to be greater than E to the power of epsilon squared, and so on. So at the end of what I get is this equation of the following form: A plus all the elements which are distance 1, and these are the combination of n elements taken 1 by 1, time all the possible ways to change their values, times A with epsilon, plus all the elements which have distance 2, and these are combination of n elements taken 2 by 2, times all the possible ways to change the values to elements, and this is A epsilon squared, and so on. Okay? And this is smaller or equal than 1. So if I rewrite this equation, I can bring outside A and write, oh, I'm sorry, this is not n, this is U. It's the number of possible individuals. So this is A for the summation of K equal from 0.
Can you just see the result? Because I don't think anybody is following in detail these steps.
Anyway, so at the end we get that A is smaller or equal to, so this is the binomial expansion.
The standard type of stuff. Leave it as an
Yeah. And notice that this A is the bias, it's the same, is the expression max P of Z given X, which by the way I forgot to say that it corresponds to the bias disk. So A is essentially gives this, once it's divided by n, of course. And so it's exactly this divided and then multiplied by n. So this is expresses essentially the leakage. But
let's see, U is the number of individuals.
yeah.
So that may or may not be large. And V is the number of values. What does this mean if V is not discrete? I guess you have different ways of getting the value.
If the V is not discrete,
It's not a discrete variable, it still has a expression like this.
so yeah.
We were talking about things like height and so on,
This
right?
is
Yeah.
So you really did this for discrete variable.
this is
Yeah,
anyway.
so the value guys in the database there is so. There are no logs here. Logs.
Yeah. So if because I took away some pieces, so the full expression is that I, so the information is smaller or equal to the, so this was, I have to take the entropy of the entries minus the log of this quantity, right? So it will be U log, oh, I'm sorry, this B is not here. Comes now. Log of B, yeah, the power of
Okay,
epsilon.
now it makes more sense.
Okay, so the V comes from the fact that I have added the entropy of the input.
No, sorry, you really mean that V there?
Yeah, yes, because this is x minus h infinity of x given z. So this is, I mean, this a log of a is this part, and this is log of v at the power of u.
So epsilon is usually small, right? V is usually big.
Yeah.
No?
Usually, I would say U is number from the US, but that can be big. It depends really on what you are really considering. But it's in general big is
Okay, so let's assume V is big. So then this becomes e to the epsilon.
Yeah.
Okay.
And this bound is strict because the same construction will give you the matrix with exactly this bound. I mean, so here you have, you put exactly the values, these values, then you get exactly the liquid.
So we get bounds, we use the same transformation and get for all these bounds?
Yes, except that the bound on leakage for an individual is a different shape, but it's essentially the same reasoning. And the interesting point is a question number 4. Okay, so these other questions are dealt with essentially in the same way, except that the structure of the graph might be different. So when we consider utility now, we consider a graph yx that where the adjacency relation is induced by the graph structure of x. So essentially what we say that y is adjacent to y prime if y comes from an f of x and y prime from an f of x prime and x prime are adjacent. Okay, so we consider now the graph structure induced on y, and under certain conditions we are able to make the same construction and construct the bound and also the optimal h. So these additional conditions, okay, so y could have exactly the same structure as x, or could have some other properties like
Oh, I see. So the nature of f will reflect in the structural properties of this new graph.
Yeah.
so essentially what we have done, we have studied some properties. One is the vertex transitivity plus plus. Another one is the property of being a distance regular.
So you don't know that Vt plus plus is actually different from Vt.
We don't know.
This is what you asked me yesterday.
Yeah. So anyway, what we have done is to study some particular kind of structures that y might have. And this is then put on the query. And we have some examples in which we show that this outperforms indeed the other constructions that were done in the past.
Distance regular for sure they are not the same as Vt plus plus.
Yeah, sure.
Oh, distance regular? No. It's
No, of
very
course not.
different property. Okay.
Oh, thank you. Any questions? Answers to proofs of convection? Anybody know how to prove that Vt plus plus is the same or not the same as Vt? Julia? My graph theory, not graph theory, group theory oracle.
Utility is
I'm sorry, they didn't say what utility is. Utility. So there is a standard definition of utility. And it's defined in this way. So if you have a channel like this, so 1, 2, 3, of H, so the utility between Y and Z, is defined as the summation of okay, so first of all, you have to specify not only H, but also two other things, namely how you are going to guess, to make a guess about, to make a bet about the real value, the input. So we assume a function z from z to y, which we call the guess function, which remaps the output into the input. So that's what is the best bet, or what bet you make when you see when you see a certain z. What is the y that you guess, in which you bet. Okay? And then you must have a let's call it gain function, which tells for every pair x and x prime, sorry, y and y prime, what you gain when the real value is y and the value you guess with g is y prime. Okay? So now, the utility, the global utility is defined as the summation on all possible y and z of the probability to get z, to get x and z, so you give input y, and you get output z, so you get probability, times the gain of y if you guess g of z. And we have studied the particular case of binary gain function, which means that so gain x, y, y prime is 1 if y, the value guess is exactly the real one, and 0 otherwise. So either you win everything or you don't win anything. And in this particular case, well, the reason why we have studied this is because this is exactly the bias, the converse of the bias risk. So it's, if this is binary, sorry, assuming that the guess function is the best thing you do, and you apply the map rule, then this coincides with the max overall y. Which is the bias risk, the converse converse risk. And is also related to
so the truck is here. So let's thank Catuscia again. Grab food before the truck disappears.